Our next speaker is Dr. Gazey. Rose is a member of Pure Energy Centre, one of our lead partners in GenCom, looking at the bio to hydrogen plant in Stornoway, and it's a closed circle economy where they're using all of the energy generated and utilised within the project and using also all of the other byproducts such as oxygen within that. Ross's career in hydrogen and renewable energy spans almost 20 years in designing, developing, implementing and operating hydrogen and renewable energy solutions for customers. He has been responsible for the technical delivery of the first renewably powered low and high pressure hydrogen refueling station in Scotland. In addition, he has been the technical lead in innovative pan-European projects developing smart mobility, smart grid, electric mobility, hydrogen transport infrastructure and innovative hydrogen safety solutions. He maintains an active link between academia and industry in applying the latest innovations to meet customer needs and has been author and co-author in over 25 publications, including the Elsevier Comprehensive Renewable Energy 2012 reference modules, and most recently, the Elsevier Renewable and Sustainable Energy Review Journal. Dr. Gazey is, as I said, the key partner and the key lead in our Pure Energy Centre project. It's run by Elizabeth Johnson. And remember, one of the things when we developed GenCom, it's generating energy security for remote communities. You're not going to get much more remote where Rose is at the minute. You look at him, he's well wrapped up for what is a mild winter so far. And one of the starting facts I remember Elizabeth saying to us, whilst they're based way up in the Hebrides, the capital is Edinburgh. They look to London for their leadership because that's the government. The closest train station is Bergen in Norway, and the closest capital is on the Faroe Islands. So it shows how remote they are, and hopefully that energy remoteness comes across in Ross's presentation. Dr. Gazey, bio to hydrogen, over to you, please.
Thank you, Paul. Just a small correction there. We're in Shetland, so whilst the project's across in the Western Isles, we're up in the Shetland Islands, so in the middle, if you like, from where I'm sitting anyway. So we're going to look at bio to hydrogen and how that's been used in an innovative way in a project in the Western Isles on the west coast of Scotland. First of all, I thought I would let the listeners know a little bit about the Pure Energy Centre, then take a look at the integrated energy system, and then go on to look at how taking biomass to hydrogen has worked in practice, and then some key findings. So Pure Energy Centre has been around for a while now. We've got a multidisciplinary team and have developed some extensive experience in clean energy technology integration, which you'll see as we go through the presentation. But we are actively involved in concept development, system design, and construction right through to operation and maintenance. We're quite innovative in our approach to things, and whilst we started from a small community-derived project about 14 or 15 years ago, we've slowly built up a number of innovations as time has gone by, and as you'll see, can do the production of hydrogen from a variety of clean energy sources. And as I mentioned, a sort of a one-stop shop. You can sort of see here in the left some of the storage technology. I noticed one of the questions in response to the poll was around storage, and that is a key element of hydrogen going forward, is the continued development of advanced storage techniques. So a more traditional approach to what people might consider renewable hydrogen is you have a renewable generation connected to the network, and the renewables either directly or the surplus of that generation is used to create hydrogen through a process of electrolysis. That is often stored at a lower medium pressure, and for end use applications, of which transport is a sort of a major end use at the present time, it's compressed to high pressure, stored and dispensed for that end use application. And in the previous slides, you would have seen a real hydrogen bus. So that is technology that is here and now and is currently working. But in this particular project, it's a slightly different take on the same on the same concept, if you like. So in this particular example, we have a large municipal organic waste processing plant, and it also incorporates now fish waste from a lot of fish farming and fish processing in the local area. And that creates biogas and high quality fertilizers, if you like, through the process of anaerobic digestion. The biogas is consumed in an on-site combined heat and power unit, which is used to power the plant directly, but also has a surplus of capacity. And that surplus of capacity, up to a very small limit, can be exported to the local electricity network because of network constraints. And nearby wind turbines feeds into the plant to provide some extra green electricity when required. But the surplus renewable energy on site can be diverted to a small electrolysis plant, and that creates both hydrogen and oxygen gases. And in this particular project, the product hydrogen is used for transport applications. So a refuse collection vehicle running on the hydrogen is used to collect waste, which feeds into the processing, and then an on-site fuel cell powered unit can provide auxiliary power to the fish processing facilities, and it creates a bit of a virtuous circle. So you have the need to process waste in an environmentally friendly manner, and in the process of cleaning that waste up, you can create energy which is used to support the entire process from start to finish. So in this example, there's a very modest electrolysis plant, of circa 30 kilowatts, and if running at full capacity, can generate around 12 kilos of hydrogen per day. A kilo of hydrogen has two energy values, the lower and the higher heating value, as many of the listeners will know. For transport applications, it's typical that you use the lower heating value, and where you combine the heat and power production from the end use, you can extract the higher heating value. So in simple terms, the hydrogen electrolysis plant can capture circa 146 megawatt hours of equivalent energy for use in the transport applications at the facility, which is not insignificant. What that roughly equates into is an equivalence of about almost 11.5 tons of equivalent road fuel displaced, which is about a little over 13,500 litres of diesel equivalent that would otherwise have to be sourced from hydrocarbons. And that, for the vehicles, is equivalent to almost 129,000 miles of driving, if you were to measure it in distance or clean miles. And the side effect of that is that we have the potential there to save about 35 tons of carbon dioxide equivalent annually. And you can convert that into a sort of a trees equivalent. Now, this is subject to quite a significant amount of variation, but if you take a very average tree in an average location, and something like a pine tree, literature suggests that would absorb somewhere in the region of around 10 kilograms of carbon dioxide per year, and at a fairly standard sort of planting density of around 1,000 trees per hectare. This very modest electrolysis plant has the same carbon saving effect, if you like, of planting around 3,500 pine trees, or about 3.5 hectares of pine tree plantation, if you like. Now, if the trees were to have been planted on unsuitable ground, such as peat bog, then you wouldn't realise such a good carbon saving from that tree planting. Likewise, different tree breeds would offer better carbon savings. But this is just averages based on what we've learned in the sort of local area around Scotland. So A few key findings from what we've observed over the last few years from the plant operating is that something that was quite innovative about it was the diverting of organic waste from landfill to anaerobic processing. That reduces the amount of unprocessed waste that goes to landfill, and therefore the emissions and carbon and methane emissions that would have come from that if it had just been dumped in a hole, as it were. We capture the waste oxygen from the electrolysis process. So in many applications where electrolysis is used to generate green hydrogen, oxygen is vented rather than utilized. And in this project, we capture the waste oxygen and put it to a use in fish farming application, where there's a significant requirement for oxygen use. By utilizing this waste product, we displace a significant amount of kerosene or diesel consumption through the use of on-site combined heat and power generation, and using hydrogen in road transport applications as well. By managing the on-site energy generation, we minimize the impact on the embedded generator on the local network. So in a lot of remote parts, embedded generators can have a significant impact on the local network, electricity network, and by managing that generation by the application of the hydrogen technology, the network constraints can be better managed. Number of benefits that can be realized to the local economy when you take a more holistic approach from a clean energy project, and that is to help secure continued development of the waste industry in the remote community. So rather than putting it all off island, as it were, for processing, it can be processed locally and provide local benefit. There's a better handling of organic waste in the remote community, and as I mentioned in an earlier slide, you have a byproduct of high quality nitrogen enriched fertilizer from the output of that anaerobic digestion process. There's a requirement to handle both the oxygen and the hydrogen, and that creates some work locally within the local employment market, and it helps stimulate the development of new hydrogen supply chains that can support the adoption of hydrogen vehicles and so on. And mentioned in a previous slide, there's a sort of innovative part in this anaerobic digestion plant, and that's the introduction of fish waste. In remote parts of Scotland, there's a significant employer in fish farming and aquaculture, and it's estimated that they consume maybe around 40 gigawatt hours a year in the area, and the hatchery sites as well have a significant requirement for low levels of heat, which equates to a significant amount of energy across a year. And fish waste from the operations and processing has the potential to generate around 60 gigawatt hours every year, which would cover those energy requirements and further close the circle, if you like, for the new energy required into the process. So that is a very brief overview of bio to hydrogen and using the plant in the Western Isles as a case study.
Ross, excellent presentation. Many thanks. I think you take this maybe as a compliment. Hopefully, you understate what has been achieved, and that you've developed a wonderful circular economy there. And one of the great phrases you came out with, you have 129,000 miles equivalent of diesel saved, and you use the phrase clean miles. So if somebody is doing an average 20,000 mile a year, that's 6.5 years of transport on a personal car.
Yeah, on average.
When you put it in the lay terms, if we use the phrase that you used, you're saving 35.7 tons of CO2 equivalent annually. But bring it down to something that people can benchmark against. It's 129,000 miles, equivalent to 3,500 trees being planted, the carbon saving. And you've developed that circular economy. For folks, the bio-to-hydrogen plant is one of the 3 pilots in GenCom. We have bio-to-hydrogen run by Pure Energy Centre. We have solar to hydrogen run by ETSIS and Dr. Bodo Ghost and his team in Germany. And we have wind to hydrogen run by Energia and Mark Walsh and the team in Northern Ireland. It's 3 different scales of renewable hydrogen production using electrolyzers and hybrid opportunities for application covering industry, transport, solar and heating. And it looks at developing that model where we have that hybrid mix. And at the back end, then we have the decision support tool led by Dr. Rory Monaghan in Galway to allow people to make informed decisions based on the data from the 3 pilots. The first pilot that's up and running is the bio to hydrogen in Stornoway, and it's getting excellent results. As Ross says, it's not just saving energy, it's reducing the carbon footprint, it's energy neutral in the whole plant, and they're using the opportunities that are coming out of the back end for other opportunities in the fish waste. A question there for you, for Ross, from Mark Welch, one of the partners in Energia, is you're using the oxygen in the fish farm, but have you looked at the oxygen for wastewater treatment?
Not at the moment, to the best of my knowledge. At the moment, the oxygen is to be used in the aquaculture.
Yeah, and it's fully utilised in the aquaculture to reduce that.
Yes, because one of the feedstocks, if you like, to the start of the process is the fish waste.
Yeah. And a question from Dr. Bodo Ghost. How do you, Ross, see developments in the field of new electrolyzer technologies, such as AEM electrolyzers? What is your opinion of the state-of-the-art AEM electrolyzers, and where do you see the technical advantages in this technology? Coming back to the core of today's talk is innovation. Where do you see the technical advantages in new AEM electrolyzers?
So in the example given in the presentation, it was an alkaline electrolysis plant that's used. AEM electrolyzer against that would offer the benefit of not having a liquid electrolyte to manage in the same way as you do in an alkaline electrolysis plant. But they're not quite as efficient at converting the energy into hydrogen out. They offer a lot of promise, but at the present time, their scale is really quite small, maybe 3, 4, 5 kilowatts as a module, if you like. So I think they've got a lot of potential for sure, but they're in the kind of earlier commercial stage, if you like, whereas alkaline technology has been around for a very long time and is quite a well-established technology base.
It's also to say this is just one project Pure Energy are in and one electrolyzer. You have numbers of other electrolyzers.
That's right.
Applications.
That's right, yeah. And typically we look at alkaline electrolysis technology over the other options just because of its more tried and tested presence, and it's got a lot of time served in industry and industrial applications compared to PEM and AEM. So electrolysis is the longest served, if you like. PEM is probably catching up the fastest, and AEM offers a lot of promise as a kind of an intermediary between the two technologies.
You will realise, of course, that the question from Bodo was loaded because
for sure.
Developing the solar to hydrogen, Bodo and Wolf Clements are including 2 electrolyzers in that plant so they can compare and contrast and inform the decision support tool. So yep. he's looking to pick your brains to get better moving forward. Ross, many thanks for your presentation. Can I also add, folks, the presentations were available to all the registrants later on, but also Ross's case study will be in this quarter's H2Go News, the GenCom newsletter. And Ross is putting together that. And it literally benchmarks it simply, where here's the tons of CO2 equivalent, here's the comparisons in miles, diesel, and trees. And it brings it to a level where people can get a grasp on it. With what, as Ross quite rightly said at the start, it's a modest electrolyzer, but it's meeting the energy needs of that environment, of that situation. And it shows the approach of GenCom, where it's that hybrid mix where we can compare and contrast, and people then using the DST at the back end can see different scales, different applications, different renewable sources, and how they can integrate and mix.
So, sorry, Paul, there's a question about efficiencies just on the chat box there, and the reason it makes more sense in this project is because it's quite highly integrated. So when you're talking about efficiency, the alternative would be a diesel generator sitting out in a remote facility, and that diesel then has to have diesel burnt in order to get that diesel to the site to provide the energy for the the plant. So whilst I do take the point that if you use electricity to make hydrogen, to store it, to then make electricity again, there is an efficiency loss. In this particular example, it's using the waste outputs from that process to make the hydrogen to generate that on-site power as and when needed, which is still got a better environmental footprint than burning diesel in an on-site diesel engine.
I was trying to keep that question for the final Q&A because it's a great question, but we
sorry, Paul.
Folks, keep more questions coming in because, as you can see, Ross is in good form to answer your questions. You have the opportunity to get questions to Matthew, Diana, Ross, and to Blas, so feel free to keep the questions coming, please. Ross, thank you very much indeed.
Thank you.